Hello everybody, welcome back to this training on neural networks and deep learning. In this video, we will look at some of the analogies between the way neural networks are constructed using the fundamental building blocks and logic gates. By the way, the reason I am drawing the reference of logic gates here is because there's a very nice intuition which gets developed out of this comparison, and also logic gates are something that the basic concepts of logic gates almost everybody is aware of. Either people would have read it as a part of their computer science lessons, or as a part of the Boolean algebra lessons in their maths. But nonetheless, if you still are not aware of logic gates, if you think that this is something which you're not comfortable with, then feel free to skip this video of the entire series. And if you do so, you're not going to face any problem, or you're not going to struggle in understanding the subsequent videos. Okay, so what did we look at thus far? So in the previous two videos, we started off from the very basics of the concept of neural nets to the extent that we defined something which is called the perceptron, right? And it was the most fundamental building block of a neural network. And then we looked at how perceptrons can receive information from different sources and then combine them to arrive at a final decision. And then we also intuitively reasoned out that if one single perceptron can do simple decision making, then when it comes to more complicated decisions, a system of perceptrons must be able to handle them. And then in the second video, we constructed a system of perceptrons in a way such that they can handle complex decision making, and this arrangement of a system of perceptrons together actually gave rise to something which we called as the feed-forward neural network, which is the most common variant of neural networks that we use. And then very briefly, we touched upon the concept of activation function in neural networks. So we looked at the mathematical representation of how a neural network does decisioning. And in that context, we looked at the concept of activation function. So with that as the premise, we will now look at how how and rather why neural networks can handle almost any decision-making task. This is the structure of the feed-forward neural network that we constructed by combining the individual perceptrons, which we called as the fundamental building blocks of neural networks. So what we will do out here is we will zoom in into one of the fundamental building blocks, and once again see how the individual building blocks perform the decision making task, and then try and draw an analogy with the logic gates. So, in order to zoom into one of the particular perceptrons of the network, let us go back to this example, and I'm sure you recall this example because this is what we started with in the first video. So in this example, we are talking about a decisioning task, and the decisioning task is basically to decide whether or not you want to go to an event in the town which is happening in the evening, and the event happens to be a food festival. And in order to decide, there are three factors that you were considering, right? The first factor was how will the weather look like in the evening? Will there be rain? And the second factor was what company will you have if you go. So is your fiance, your girlfriend, or your boyfriend willing to come along to the event? And the third factor was is there parking space nearby to the event venue. So we'll look at the same example, except for we will strike out the third factor here for the sake of further simplicity. So we'll assume only the first two factors are present in the decision making process. So essentially, in this case, there is a single perceptron which is receiving two pieces of information. One is about how the weather will look like, and the second one is about the company that you're likely to get, and all of these are binary informations, right? So it's either a 1 or a 0. So the weather will either be good or bad, and in terms of your company, either you will get a company of these people or you will not get. So these are binary information that the perceptron is receiving, and then it's combining it in a way to arrive at your final decision. And how does the perceptron combine this information? As we have seen before, so it calculates a linear combination of the input factors, and then does something like this. So W1 and W2 are the weights, and V is the threshold with which the comparison is made. And the decisioning rule goes like this. So if the linear combination W1x1 plus W2x2 exceeds the threshold, then you decide to go to the food festival and you ditch the plan. If this linear combination W1x1 plus W2x2 is less than equal to B, right? And for the sake of representation, let us call this expression on the left hand side as Z. That is what we will write it as in the table. And uh, as we were doing previously as well, instead of estimating the W's and the B with some appropriate method, we were actually making a specific choice of W and B to see how the decision making works. And actually the decision rules or the decisioning system, what kind of decisions you arrive at depends very much on the choice of the W and the B that we have seen before. So in this case, we will make a specific choice of the W's and the B's. So we will choose W1 and W2 both to be -2, and we will choose B to be -3. Now with that choice, and if we look at all possible combination of the values of x1, x2, which are the two factors that we are considering here. So one of the factors is how will the weather be, and the other factor is whether or not you will have good company. So uh, there are four combinations possible here for x1 and x2. These are binary factors: 1 0 0 1 0 0 and 1 1. And for each of these combinations, if we work out the value of z, which is this linear combination, so obviously if either one of x1 and x2 is 1, then the value is -2, because both the weights W1 and W2 are -2. If all x1 x2 are 0, then definitely z is going to be 0, and if x1 x2 are both 1, then we get z to be -4, and b is the constant threshold, which is -3. So if you compare Z and B, and then jot down here in the last column what the final decision is going to be. So we see that in the first case, when x1 is 1 and x2 is 0, Z definitely exceeds B, so our decision is yes. And so is the case for x1 equal to 0, x2 equal to 1, and also when x1 x2 both are 0. However, when both the conditions are 1, x1 and x2, then Z takes a value -4, which falls short of the threshold -3, and hence the decision is no. So essentially what is happening is, with this particular choice of weights that we have taken here, uh, the decision is always yes, uh, except for the case when both the factors are positive, x1 and x2, right? So that is what it turns out to be here for this particular choice of weights. Obviously, by tweaking the weights, this scenario will change. Now, let us hold on to this outcome for the time being and see that what kind of analogy with logic gates it leads to. Now, the two tables that you see here, the left hand side table is basically the decisioning that you are getting from the perceptron for this particular choice of weights, W1 equal to -2, W2 equal to -2, and V equal to -3. And in the right hand side, what we have done is we have taken the same factors x1 x2, which are binary factors, and then computed the AND gate, OR gate, and the NAND gate, right? So x AND is x1 AND x2, OR is x1 OR x2, and NAND is x1 NAND x2. If we do that, we see that we get some outcomes, and if we inspect the outcome that we get for the NAND gate, it is very similar to the decision that we are getting by the particular choice of weights. If we assume that this yes can be coded as 1 and this no can be coded as 0, then the decision in this left hand side table is exactly equal to what we get by applying the NAND operation between x1 and x2, right? So this particular choice of weights actually is leading to a scenario where the perceptron decisioning is similar to the NAND operation. And if you recall from from the logic gates theory, that NAND gates are universal gates, right? So they can be used to generate any other logic gates. So when we used to build those circuit diagrams using logic gates, this was a familiar concept that we used to have, that NAND is a universal gate, and hence it can be used to reconstruct any other logic gate, and hence any decisioning in the circuit diagram can actually be achieved by using a collection of NAND gates. Now, what that means is that we are able to actually replicate NAND gate using perceptrons and a particular choice of weight for the perceptrons. And NAND gates are universal gates when it comes to decision making. So both these factors taken together, intuitively we can say that if we choose the weights properly, then perceptrons can actually be very effective in carrying out any kind of decision making. And if we generalize that neural networks are nothing but they are a collection of perceptrons, so which actually means that they are a collection of NAND gates organized in a certain way. So and NAND gates are universal decision makers. So that would lead us to believe that even neural networks can be universal decision makers, obviously with the right choice of the weights, right? So that's a very good intuition, because we see that these days neural networks are used in a very wide variety of use cases, be it digit recognition, be it image classification, or be it language translation. So, so neural networks have a very wide applicability, and that is possible because neural networks can handle almost any decision-making task if we construct the network in the proper way and choose the right kind of weights. So there must be there must be an intuition that why is that the case. So one of the intuition, which supports that observation is what we have just seen. So it's a great thing to have, but at the same time, as much as I'm saying that it's a great intuition to have, it also raises a question, and the question it raises is, if perceptrons actually can replicate logic gates, universal logic gates like the NAND gate, by a particular choice of weights, the neural networks essentially are nothing but they are some kind of combination of universal logic gates, right? So what's the big deal about it? Because then we are not talking about something which is fundamentally new or fundamentally different. We are actually talking about logic gates which have always existed in the circuit diagrams. So is that the case? So then are they all but the same? So that question becomes quite natural. Well, the answer to that question is even though there is an analogy, there is an intuition, but they are not all but the same. So if you look at the logic gates or the circuit diagrams, typically this is how they look like. What happens in a circuit diagram is if we have, let's say, three inputs here, A, B and C, these inputs are fed into different logic gates, and then the logic gates do their respective operations and then pass on the signal to the next logic gate, so on and so forth, and finally the circuit gives output which is Y, right? Now in this entire process, as the information moves from one gate to another gate in the circuit diagram, there are no weights or no transformations applied on the on the information. So for example, if A is being fed into this particular logic gate, and then this logic gate is doing some operation and then passing on that information to this logic gate, the output uh, from this logic gate that I'm pointing at is what straight away gets into as an input to the following logic gate that I am pointing at now. There are no weights involved here. There are no other mathematical transformations involved here, right? So logic gates simply, they are stacked together in a circuit diagram, and the uh, output from a logic gate actually flows into as an input to the next logic gate. Uh, no other tweaking is involved in the information. But when it comes to neural networks, it's not that simple. So if you see the diagram on the left hand side here, the input factors or the input features, they are first fed into the neurons in the first layer or the first stack, and then these neurons, they do a lot of operations on this factors, right? So they compute a linear combination, and then if it is a perceptron neuron, then there is a particular kind of activation function which is applied to get the output, and then that output is fed into the neurons in the subsequent layer. So there are weights involved in each of these connections from the input feature to the neuron, and then subsequently from the neurons of one layer to the neurons of the next layer. There are weights involved which are used for combining the information. No such weights are involved as far as circuit diagrams are concerned. And neural networks, the weights which are involved are actually estimated from the data using which the network is trained. And how the weights are estimated? Obviously in a way that the final decision that we arrive at is as much accurate as possible. So there has to be some measure of error in decisioning, and then the neural network will try to minimize that error given the training data, and by minimizing that error it will estimate the weights which are connecting the input factors to the neurons in the first layer, and then another set of weights which are connecting the neurons in the first layer to the neurons in the next layer. So long story short, even though intuitively we drew an analogy between neural networks and circuit diagrams or logic gates, but they are not all the same, all but the same. There is a subtle difference which we just now discussed. So that brings us to the end of this video where we looked at this analogy. As I said in the beginning, this is just for the sake of intuition, and you might skip it as well. It's not going to be any problem in watching the subsequent videos from a continuity perspective. In the next video, we'll actually dedicate that to activation functions. We briefly introduced the concept in the second video. In the next video, we'll have a detailed discussion on activation functions and what is their significance in the context of neural networks. So thank you for watching this one, and stay tuned for the next video where we discuss activation functions. Thank you again.